So far we have looked into reflection and refraction, which govern the macroscopic interactions of light with matter. Now we will venture into the realm of diffraction mechanisms, which govern the microscopic interactions of electromagnetic waves like light. The learning objectives for this video involve obtaining a basic understanding of the diffraction of light. We will discuss the concept of interference and apply it to electromagnetic waves. Finally, we will derive the wave equations for superimposed electromagnetic waves. As we trail towards some of the more complicated quantum mechanical properties of light, it's good to know that every cloud has a silver lining, a phrase coined by the English poet John Milton in 1634. Silver linings are a phenomenon well demonstrated by this picture of the sun, hidden by clouds. But why do clouds have a silver lining, and which properties of light underlie this phenomenon? The silver lining of cloud is an example of diffraction. This illustration shows that the direct light beams propagating through a cloud will be absorbed. Only the beams at the edges of the cloud are diffracted towards the observer at the ground. The edges of the cloud therefore appear bright white. Diffraction can be defined as the bending of light around an obstacle. Diffraction can occur when the light encounters particles that have a size of the same order of magnitude as the wavelength of the light. A cloud consists of many water particles. The illustration shows two such water particles in dark blue, partly blocking an incident light beam. The light wave will propagate between the water particles. The area between the water particles will actually function as a point source, from which the light wave will propagate in all forward directions. Therefore, a fraction of the initial light wave will be diffracted towards an observer on the ground. This point source function of the area between the water particles is better illustrated by the single slit experiment. In this experiment, a uniform light beam propagates towards a solid wall containing a single slit. The colors represent the amplitude of the electrical vector of the wave. The slit has a width equal to the wavelength of the incident light. We can clearly see that the light propagates in all outgoing directions. The intensity decreases with increasing angle from the normal. The single slit causes a familiar wave pattern of light intensity on the black wall. This pattern in light intensity is shown on the right. But what happens when we introduce a second slit, also with a wavelength sized width? What we see is that the two waves start to interfere with one another. The uniform outward moving half circles are now broken up into peaks and troughs. These peaks and troughs also appear on the black wall. We find the same familiar pattern of light intensity, but now broken up into bright red peaks and dark troughs. This phenomenon is known as interference. Interference occurs when two different waves occupy the same space at the same time. We call these waves superimposed. This figure shows two superimposed waves moving in opposite directions. The resulting wave is depicted by the green line. We can see that the amplitude of the superimposed wave is sometimes greater than and sometimes smaller than that of a single wave. When the peaks of two waves are perfectly aligned, they are said to be in phase. Two waves in phase exhibit constructive interference. The amplitude of the peaks and troughs of the waves will then add up. When the peak of one wave aligns with the trough of the second, they are in antiphase. Their amplitudes will then cancel each other out. This process is called destructive interference. The interference of electromagnetic waves can be explained by the wave equations of two plane harmonic waves. Look at two waves, A and B, that have the same wavelength and cover the same portion of space. The letter phi denotes the phase shift between A and B. K is the wave number and omega is the wave frequency. We can superimpose the two waves by simply adding them up. C in this case is the wave resulting from the superimposition of waves A and B. The superimposed wave C can be described by the following relation. The amplitude of the superimposed wave is therefore equal to the amplitude of wave A plus the amplitude of wave B times the exponential of the phase shift between A and B. We can see that the amplitude can be stronger or weaker than A and B depending on the phase shift. When phi is a multiple of 2 pi, the amplification will be maximal and constructive interference will occur. If phi is in antiphase, however, the wave exhibits maximal attenuation. This occurs when phi is an uneven number multiplication of pi. The waves then exhibit complete destructive interference. By cleverly designing the solar cells, we can use the concepts of constructive and destructive interference to our advantage. Exactly how interference is used in solar cells will be discussed in the next video. In summary, we define diffraction as the bending of light around an obstacle. We looked at the famous single slit experiment and saw that opening a second slit will lead to wave interference. A phase shift of 0 or a multiple of 2 pi leads to constructive interference. A phase shift of an uneven number of pi's leads to destructive interference. Finally, we derived the amplitude for superimposed waves in the case of constructive and destructive interference.